Welcome to ProAmp Solutions. We have a real treat in the shop today. So this amplifier was entrusted to me by the owner to go through and make operational again. This is an example of what has become known as woodies, and very early after the K&F company was dissolved, Leo Fender, these were the first amps that were made, and so most of them have 3 bands in the front. This one I think is quite unique in that it has the 2 bands. It appears to be all original. This is a walnut cabinet, and this one just at first glance, so I'm just getting my first look at it right now, but I'll give you a closer look here at the face of it, and then we'll flip it around and see what's in store. Okay. Alright, so we have the Fender with the lightning bolt logo, Electric Instrument Company. This is serial number 210, and this particular faceplate was used on the Model 26, what was called the Deluxe. But what I'm seeing inside does not coincide with the Deluxe as it became known. This one has a 10-inch speaker, and you can see the field coil down here. So this is the 10-inch field coil, and it's what I don't see that I would expect to see if it was a Deluxe: a pair of 6V6s in push-pull and a different tube configuration. The earliest Princetons were a different configuration, and so what I think we might be looking at here is something that Leo may have worked on himself as a transitional model, because there's a rectifier tube I can see behind the power transformer here, and it's got a Tungsol 6SC7, which makes sense. That's the opening gain stage tube. But then I see something very interesting here, a 6J5 and then a single 6V6. So it's going to be really interesting to open this one up and take a look at its state. It does appear to be completely original. This has the original 2-prong power cord on it, and yeah, I'm really excited to work on this and take a look, see what kind of condition that it's in and why it may or may not be operational. So I'm going to very carefully remove the chassis, and we'll get a closer look. I'll be right back when I have it out. Okay, I've got the chassis removed so that we can take a little bit closer look inside the cabinet, the construction inside. Take a good look at this Jensen 10-inch speaker, which looks to be in really good condition. A little bit ratty inside, but this is the connection to the chassis. And this, if you can see this up close there, not great connections inside the connector, but everything, I'll have to take a little bit closer look, but everything looks to be in order here. So let's pull up the chassis and take a look at that. Give me a second. Okay, so what we have here is a really, really interesting piece of history. I'm a little taken back. So, as I understand the history, the very earliest Fender amplifiers were a Princeton designed for steel guitars, and they had an 8-inch field coil speaker, no plate, no markings, just the control knobs, and it did not have an on-off switch. You plugged it in and it was on, and it was a 3-tube configuration. Then the Deluxe, the next evolution, was known as the Model 26. And this here has the Model 26 faceplate. And we can see this is serial number 210. Sorry about that. Move this back. Serial number 210. It's got the control indicators that go from 1 to 12, 2 instrument inputs, and a microphone input, which is consistent with the Deluxe. However, the Deluxe was a 5-tube configuration with 6V6s in push-pull. This particular amp only has one 6V6, a 6SC7, and a 6J5, and of course the rectifier. So what I have to believe is that this is a transitional model, part of the evolution of the earliest Fender amplifiers, originally designed for steel guitar. And I'm just kind of blown away, because it's clearly not the Princeton, and it's also clearly not a Model 26 Deluxe. It is a tweener, so to speak. So what I believe this, I'll have to look up, but memory serves me correctly, this 6J5 is a single triode tube. So it looks like it's driving the 6V6 single-ended, and it looks like our input gain stages as the dual triode 6SC7. So it looks like we have a hybrid here. We've got what looks like to be the Deluxe input section and closer to the Princeton single-ended output section. So this one's interesting. It has the 10-inch speaker, the 10-inch field coil speaker, but is not the push-pull configuration. So basically, as I go through this amp, I'll blueprint it as built, and I think what we're going to have to do on these capacitors is I'll do my vintage restoration treatment on them. I'll carefully unroll one end of these, and we'll take the cans out. We'll clean them out from their contents. We'll put a new high quality filter cap in the same can. I'll drill on my drill press really small holes in each side to put the leads through, and we'll retain the vintage look of each one of these capacitors, and I'll remount them in their same spaces. One thing that concerns me just a little bit is there is a level of rust and corrosion on the chassis here. So when we redo ground connections, I'll have to clean that area up so that we have really good grounds. And then of course I'll leave the death cap installed. We'll take one leg off and put heat shrink tubing on it, and we'll install a 3-prong cord that is grounded to the chassis for safety. Basically, if I work on a vintage amp and they don't agree to do that, I will not work on it. So we're going to put as much of a period correct, authentically looking 3-chord prong in here for safety. And then I'll start evaluating the rest of these resistors and capacitors to kind of see if we need, how far we need to go on beyond these electrolytics. But for sure these bypass caps are bad. I can visually see quite a bit of leakage, especially on these two, and we know this one's bad. So I think that will be what I'll do next. I'm going to blueprint this amp as built, what the schematic is, what the exact value is, both based on the color bands and then what we actually experience, to see how much drift there may be. And if one is really out of tolerance, we may change it, but I'd like to leave all the originals in here if at all possible. So I think I'm going to, yeah, I think the first step really will be to blueprint this amp and exactly understand its schematics. So again, we've got rectifier tube, preamp tube, a single triode driving a single-ended amp, and then here we have our connection that goes to the field coil speaker. So yeah, very interesting. Obviously, we'll put the tubes on the BK747 tube tester and make sure that, see what kind of state they're in, hopeful on those. But wow, what a piece of history. I have to believe that Leo may have built this himself, because it's clearly a transitional model. What a treat to see, and I'm looking forward to getting this operational to see what it sounds like. Stay tuned. Okay, I thought we would take a closer look at the tubes that were inside of this. Let me focus here so we can see a little better. Okay, so this is the input stage. This is a Tung Sol 6 SC7 GT made in USA tube, and this tube on my BK747 tests perfectly, so excited about that. So next we have the single triode, and this is a 6J5 tube. This is made by National Union, made in USA, long life. So this is a single triode. This also looks like it's got bottom getter down here. This also tests good on my BK747. Then the power tube. This is a Sylvania, made in the USA, and this is a 6V6G tube. So also made in USA, and this tests good on my BK747. And then lastly, we have a sorry, let me get you right tube here. We have a Jan CKR Kenrad 5Y3 GT. So 5Y3 GT, this is the rectifier tube, and this one also tests good. So we have 4 good tubes in this amp. That's exciting. So I've just put blue tape on here so I don't get disoriented on what was where. So I'll get on next to blueprinting the amp so we can see right now. I'll show you the number on this transformer. So the number on the top on the iron is 391549, and on the bell housing cover it says R-5406A. So yeah, this is really interesting. So again, a closer look at the face panel for you, and then you know, the gut shot. And I'm struggling a little bit as I look at the input, because some of this just really doesn't make sense. I know on the early Princeton they went through a capacitor to the input, the grid of the first tube, to block DC, maybe from any instrument. Basically it was a DC block. This makes no sense whatsoever to me. And maybe this was experimentation. Maybe that's why this lead is just kind of flying here and this is cobbled together. Because at face value, if you take 100K and then you have a capacitor of 0.03 UF to ground, that's a low pass filter, and that's like at 53 Hertz. So that would basically block most of your audio signal. So that makes no sense to me whatsoever. And then you know, what I'm guessing is this was probably attached right here where the wire is coming out to be DC block, which makes a lot more sense. And maybe this was moved out of the way and maybe this lead was actually flying at some point. Not quite sure what's going on there, but I'll document this as it is. But this just does not make sense to me how it's hooked up. So, but anyways, several fairly simple, straightforward. There's not a lot of components here. This will be fairly quick to document. So I'll get to that, and then we'll look at the as-built on this compared to the primitive, the early Princeton schematic, and also the Model 26 schematic, and we'll see how this was kind of mashed together, so to speak. Okay, I'm back and wanted to go over a progress update. So I have everything tested, and I've documented the schematic completely, so I know exactly how everything lays out. And then I have installed the new 3-prong power cord here. I've applied heat shrink on this side here, several layers, so it can't pull back through. And then we have I redid this ground connection here in the corner, cleaned that up with a Dremel tool, and got a real nice ground there. So we got a grounded power cord, and then we go through the neutral, through the fuse. I replaced the fuse. There was a 3-amp fuse in here that was really corroded, so I put a new fuse in, and then on to that side of the transformer. The hot side is switched into the transformer, and then this is the death cap. So the ground side is attached, and the other side here I've put heat shrink on, so it is no longer in circuit but still present in the amp. And then I put heat shrink on the center tap to the heater, and then the cap that was here that was dissimilar than the rest of what's in here, didn't look kind of like it belonged and didn't make sense in the circuit. It was actually, all of this is twisted together here, and this was a really solid ground connection here. That capacitor was just barely tacked in. It almost just came off, so barely tacked in. It also, all of these Mallorys tested good. I was surprised, right, almost dead on. This one was 21 nanofarads. This one was 23 nanofarads. I believe this one was 21 nanofarads. Just beautiful. So we're going to be able to, of course I don't know yet if they would have any DC leakage, but their capacitance is right on. Every resistor in the circuit was well within tolerance and will make sense operationally. So I'm actually really happy. I think this amp is going to just work as I get these electrolytics done. So at this point we've got a 3-prong power cord in where safety comes into play, new fuse, heat shrunk these areas that were kind of precarious to touch to ground. So that part I'm done with. So I'm going to do my vintage restoration of these 6 electrolytic caps, and I may clean up the connector leads that go into the socket on the other side of this. Other than that, I think this might be operational as soon as we fix the electrolytics. I'll go over the schematic with you in detail next, because this is clearly a transitional model. It's very unique. It may be the only one that exists, but it definitely has the Deluxe front end, and then it has a 6J5 single triode driving the single-ended 6V6. So yeah, I'm really pleased that all of the vintage components, other than these electrolytics, are going to remain. It will be basically, other than this power cable change, will remain completely as built and untouched. And then I've got Sprague Atom 10 microfarad caps to replace these 3 10 microfarads. I've got a Sprague 8 microfarad to replace this one, and then I've got 2 F&T 16 UF 475 volt caps to replace these two. So those will be inside these containers. So this should look exactly the same basically when I am completed, and we'll move on from there. So next step, before I actually do the cap work, I'm going to clean up my hand-drawn scribble schematic that I've got here, documenting everything. But I have all the resistors documented as they're banded. The only one that I couldn't read is this. There's a domino cap right here that I don't see any colors on the indentions. So, but it measures 607 picofarads. So this is a treble bleed cap. I'm just going to leave it in place. It tests and measures good. So it's a kind of a unique feature. I don't see this on the schematic or of the Princeton or the Deluxe, but you know, it's period correct. It's a domino style. So I'm going to leave that in there, and we'll go over the complete schematic from the inputs to the outputs, the field coil. I did test the speaker, so I put my LCR meter on it, put a 1 kilohertz signal through the actual speaker leads, and the reflected impedance is 6.5 ohms at 1000 kilohertz. So it is a 8 ohm speaker for sure, and it generated a nice low volume 1 kilohertz tone. So I'm pretty confident in the speaker in the field coil. Like I said, I'll redo this, but let me show you. So the way this field coil setup works, and I'll do a better job documenting it. It's just, again, my scribble. But basically from the reservoir cap, it's filtered. So you got a 16 UF cap for the reservoir from the 5Y3. That goes into the field coil, which is wired in series with the output transformer. So this comes through, and then that goes to the plate of the 6V6. This field coil, the primary side of it is 2.46K. So this acts as a choke, actually. So when this returns, this comes back as a choke. So this is a choke capacitor filter with 8 UF. And then we go down through 25K, filtered again to a 16 UF. And anyways, we're double filtered there through in essence a choke, which is going to be really good. Give a nice clean power supply to this. Is what goes to the screen of the 6V6, and then the same thing that supplies the screen also supplies the plate resistors of the 6J5 and the 6SC7. So this is kind of how this looked. So again, at 1 kilohertz, this the impedance was 6.5 ohms, and then the primary side of the power, the single-ended power transformer, was 385 ohms. I'm not sure the turns ratio. I didn't go through the trouble to do that. Obviously, this all looks appropriate and looks like it will work. So ignore sort of my scribble here, but everything is fully documented, and I'll clean this up, and then we'll come back and go through it in detail. But yeah, I'm super excited. We shouldn't be too far away from hearing this and seeing what it sounds like. Okay, this is John. Welcome back to Pro Amp Solutions. So I've got the original Fender Princeton amp that I spoke about. First one developed in 1946. And this was a very simple 3-tube configuration with a 5Y3 rectifier tube, single-ended 6V6, and a 6SL7. So from the input, you come in, you go through the combination volume interactive tone stack through the second gain stage, which drives the grid of the 6V6. And they specified that was about a 8-watt output. So this particular amp that we're working on, think of it this way. Basically from here over, this amp is the Princeton. It is the single-ended with the field coil speaker and the 5Y3. So now let's take a quick look at the Model 26, that next evolution that has the faceplate that our amp does, labeled Model 26, but the Princeton had an 8-inch field coil speaker, and the Deluxe had a 10-inch field coil speaker, which this one has. So this one has several of the Deluxe characteristics. It's got the faceplate, the 10-inch field coil speaker, but it is unique because the Model 26 was a 5-tube configuration, a rectifier, a pair of 6 V6s, 6 SN7 cathodyne phase inverter, and a front end that was a 6 SC7. So this particular amp, what it shares about this is it has basically the Deluxe front end. So basically think of this amp as this front end here and only a single triode here driving that gain stage. So I have created a detailed hand-drawn schematic that I cleaned up from my scribble, and we'll put it here, and hopefully with the focus you can read this and see it along with me. But basically I've drawn this a little more clear so you can see how the field coil comes into play, and a little bit more in terms of the anatomy of this so that you can make determinations about things that aren't real clear, such as the power supply, the output transformer, the speaker. So I've quantified a whole lot of that, and I just did an unloaded power on test, and unfortunately in doing that unloaded power on test I found that the tone pot, the potentiometer portion worked correctly, but the switch was broken, so I was not getting any AC to the transformer primary. So I temporarily connected that so I could take the measurements, and we'll have to replace that, unfortunately. So basically the only modifications to this amp is a 3-prong power cord. So I come in with a ground and we remove the death cap. This one probably doesn't need a 3-amp fuse. Probably 1 amp is fine, but that's what it had in it, so that's what I replaced it with. And this is the AC switch that's a part of the tone potentiometer that in our case is bad. So we go into the rectifier tube. We come out DC rectified. This has 3 secondaries, 6.3 volt secondary for the heaters, the 5 volt secondary, which also is shared with the high voltage rectified DC, and then of course your plates. So unloaded, this power transformer without any load, just open, on the 5 volt side, it produces 5.76 volts AC. The heaters produce 7.14 volts of AC, and the HT plate to plate is 720 volts peak to peak. So we can kind of get an idea of what voltages we should expect, and then under load we'll see how much voltage drop we get, which can tell us a little bit about the nature of the power transformer. But ultimately we're going to know exact voltages throughout the amp that are generated with a 5Y3 rectifier tube. So let's move from the front across. So basically, as I was saying, this shares the front end, so you'll see this looks very familiar to the 6SC7 kind of up to this point. The differences are this particular one as built has 100K grid stopper resistors rather than 75K, and then the microphone input actually has a 2 meg to ground instead of a 1 meg, and then I did the banded value and then of course the actual measured value. So this one was dialed right in 1.98 megs. One of these 100Ks measured 109 and one measured I think 108.6, so within tolerance. And then the 6SC7 you'll notice the plate resistors are twice the value, and the cathode resistor is approximately half the value as what was specified on the Deluxe. So obviously he was looking for more gain here, but that's the way this was built, and so that's what way we documented it. Then we go through 0.02 coupling caps to the 1 meg potentiometers, and then we come into the 6J5. And this is biased fairly traditional. It's got a 100K plate resistor and a 900 ohm cathode resistor, which measured 944 on my fluke meter. So this basically is from here to the left the Deluxe, and we only need a single triode because we're single-ended rather than the dual triode forming a cathodyne. So basically this is where the split happens in this particular amp. Deluxe front end. Then we move the plate couples to the V6G through a 0.02 coupling cap. Then we've got a grid to ground resistor of 500K, and then our cathode resistor is 330 ohms, and ours measured actually 375 ohms. And then we can talk about sort of this is the tone control. On this particular amp, most of them list 1 meg, 2 meg. For whatever reason, this one here is 50K. You can see that, and it actually measures 50K. So we're going to leave it as built. I'm going to replace this with a 50K switched potentiometer and completely leave this as it was built. Not sure if this was a prototype, experimental, or a true transitional model that had some value to Leo as he worked through this. So field coil speaker. So I did some pretty thorough testing on this to try to quantify this particular field coil speaker. So this is a Jensen RS series speaker. It's a G10 RS, and the DC resistance of the field coil is 2.46K. So this acts as a choke. So this particular speaker does not have a fixed magnet. This field coil is energized with high voltage DC to create, it's an electromagnet is how this one works. But it also, this field coil dual serves as a choke. So I did some measuring on it. Again, 2.46K of DC resistance. So we can kind of figure out what kind of voltage drop we might expect based on the current draw. But then what's really valuable to know is at 120 hertz, which is the frequency of the rectification, how effective will this be at filtration with an 8 UF filter cap. So this is a choke capacitor filter here, and at 120 hertz the impedance is 36.9K and the inductance is 38.7 henries. So this is going to be a super effective choke filter here, even though at face value, if you just looked at this with 8 UF, you might not think it's great filtration. But it tells us something about the nature of the coil, knowing what the DC resistance is, and then understanding at 120 hertz what impedance it presents in terms of filtration. So again, 36.9K of impedance, and the inductance 38.7 henries. So you could do the math on that and figure out how good the filtration is. So it goes through the field coil, then it goes through the, so this is the output transformer. Let's talk about it real quick. So this one on the primary has 385 ohms of resistance on the primary. So that's just its DC resistance. Then what I wanted to figure out was what is the turns ratio so that I can know what the impedance load reflected back to the power tube is. So we know that the square of the turns ratio times the impedance of the speaker will equal the reflected impedance back to the 6v6. So I temporarily disconnected the secondary of the power transformer, and I put a 1 volt AC, a precision 1 volt AC signal into the secondary, and it generated a 51 volt signal on the primary. So the turns ratio of this power transformer is 51 to 1. 1 volt on the secondary produced 51 volts on the primary. So if we square this and times it by the speaker impedance, we get a load presented to the 6v6 of 20.8K. Quite a bit higher than I would have intuitively expected, but it is what it is. The meter does not lie. So this particular amp will present 20.8K load to this 6v6, and then as I said in the earlier video, I actually hooked my LCR meter up to the actual coil of the speaker, and at 1 kilohertz it was 6.5 ohms. So everything looks like it has integrity. I don't have any open windings here, and I've learned a tremendous amount by doing the diagnostics. I know the DC resistance, so I can, based on voltage and DC resistance and current draw, I can figure out expected voltages, etc. So this particular one, actually, the choke, if you will, this filter goes through a 25K resistor, and it's a RC filter here, and then the screen of the 6v6 and the plate resistors of both the front end and the driver stage are all powered by this same node on this amp. So once we get our voltage drop to the screen, that's the same thing that is presented to these plate resistors. So just walking you through this as built. The only one that I neglected to actually measure was this one, so I'll record that on my document here. But I'm calling this a 1946 Woody Transitional. This is a Princeton to Model 6 sort of migration amp, and this is serial number 210 as it was built. Once we get this to a state where I have the electrolytics completed, we can power it up without tubes. I'm sorry, I power it up without tubes, double check everything with the electrolytics in, then we'll add the tubes, and we can see what all of our idle operational voltages are, without a signal input. So that's really the next step. I'm going to finish the electrolytic caps. I've got them started. I can show you. So here's a cardboard sleeve out of, this is one of the 16 UF. So I carefully unroll the end and I push the can out, and then I'll show you the contents of, so this is 16. I number these so when I cut them with the bandsaw I can keep track of what half belongs to what. So this was the 16 UF screen electrolytic cap. I've cut this in two with the bandsaw, and here is the material inside, and you can see where the previous leakage was and evidence of that. I've gotten started on the electrolytics. I'll show you one that I actually have cleaned out, if I can find that here quickly. So yep, so this here was one of the bypass caps. So I have cut this in half with the bandsaw. I've already cleaned this one out, and we're ready for the drill press on this. We'll drill real small holes in here. So basically we'll reform this with a new capacitor in it, put the cardboard back over it, test it, and it will retain 100% of its vintage look. So that's where we're headed. So yeah, this is the schematic for this very unique amp, and I'm going to move on through the electrolytic capacitors. I'm going to get that pot, which I did not expect to be bad. I tested the potentiometer and I neglected to test that switch, and when I went to test the unloaded voltages, I got quite a surprise because I wasn't getting anything and had to figure out why. So nevertheless, we'll get that on order. Hello, this is John. Welcome back to Pro Amp Solutions. So I have completed the electrolytic capacitor restoration and reinstalled the capacitors. So 8 microfarad, 16, 16, 10, 10, and 10. So these were all done. I do have another video showing Mighty Mite capacitor restoration that you may want to watch, but basically these are carefully removed from their cardboard sleeves. I cut the cans in half, removed the old material, which is quite a dirty job. Recommend wearing neoprene gloves and taking great care. A couple of these were really dry inside, and it was very difficult to remove the old material, so one of them was particularly difficult. But anyways, you can see that it has retained a beautiful vintage appearance with the modern correct value electrolytics replaced. And then in these ground connections, I removed a little bit of material with the Dremel tool to make a really good fresh ground connection in the spot where those were previously located. So in my testing, as I was continuing to go through, I'll be particularly interested in what the loaded voltages are for basically everything: the heaters, the plate supply, reservoir. I'll be taking a look at the coupling caps to see if there's any DC leakage in them. So we'll go through this together. As I was testing the conductivity in the AC and the switch here, I noticed that this is the potentiometer with the switch on the back that was located in the amp, and this switch is bad. It actually would not turn on. So with it in the on position here, I'll put this in the tone state, and we can see that in the on position here we get nothing. So I have removed this, and I have ordered a 50K linear potentiometer with an AC switch to replace this one, but unfortunately this one is bad, and I can tell from the back of this that this is looks like it is cracked, and so yeah, we'll replace this. So the only original components out of this amp are the power cord, that cap that didn't belong. This is going to have to be replaced, and then of course the electrolytics look original in their vintage cardboard, but these all had to be replaced to be able to get this amp operational. So well, here we go. Let's try this out together. I have triple checked all of my connections to make sure I didn't make any mistakes, taking great care with this amp. But I have temporarily wired in the AC hot lead directly, so when I plug this into the current limiter, of course it will be energized. But let's so I have the tubes in it now, so let's bring it up on the current limiter and check initial voltages, and then if everything looks good, I'll switch the current limiter off. So here we go. Okay, the amplifier is now energized. So let's first look at the reservoir voltage, which is right here. and we have 400, and so it's starting to draw current now. You can see it come down. That's a good sign. It tells me that the power tube is drawing current. Let's see where this settles in. Now, of course, this is current limited. And my light bulb is just barely illuminated. So about 286 volts at the reservoir. Now this is current limited. And I'm going to go ahead and turn the current limiter off. Everything looks good here. And let's see what we get without the current limiter. Okay, so 381, so around 380 volts. So then the next stage, this goes through the field coil and comes back to this 8 megafarad, and let's see what our voltage is on the other side of the field coil choke. So we got 305.4 right now, and then across that resistor we'll come over here and we'll look at the screen, which is filtered again, and this supply goes to all of the power tubes. So 191.2. Okay, so with 100K and 500K plate resistors, we're going to see or expect quite a bit of voltage drop there. Let's check these caps, see if we have any DC leakage on them. None there, and none there. So again, these Mallory coupling caps tested good. Let's see what we have here. Nothing there. So we have no DC leakage on the original Mallory coupling caps, which is just fantastic news. And these all tested within a couple nanofarads of what they should be. So pretty excited about that. Okay, so now that we've at least gone preliminary through it, let me look at the, this is the plate resistor here. So we should see that same, let's see, what am I doing here? Yeah, so this is, so I'm seeing right now about 38 volts at the plate on the 6J5. And then, pardon my head here, we'll gotta be careful here. So this is one plate. We got about 50 volts on the one plate and about 51 on the other plate. So not completely unexpected. Let's look at the heater voltage real quick. I'll switch to AC and let's see what our loaded heater voltage is. So 5.19, really nice there. And then our 6-volt heater is grounded, so we'll look at there and we'll see what our 6-volt heater supply is. 6.5 volts. Okay, so loaded with the tubes in it, our heater supply looks great, our rectifier tube heater looks great, and we get an idea of what the voltages look like going through the field coil. Okay, so something I quickly noticed, we're hooked up to the field coil speaker. I've got the instrument volume on around 3, the instrument turned on. I get some audio, very nice, but the buzz is induced is pretty high, pretty bad. So I suspect my field coil and the humbucking coil are in phase and not canceling. So I'm going to take a look at that on my scope and we'll see if we can get that fixed, if that is correct, or find the source here, and we'll come back and I'll explain what that was, if that is the case and if it's wired correctly. I did notice on the primaries to the power transformer, those connections were just kind of cobbled together with masking tape and look like perhaps in development or testing they were working on excuse me, switching the polarity of that. So not sure, but I will for sure put this on the scope and make sure that the noise canceling in the humbucking coil is working correctly with the field coil, so that that reduces the noise as much as possible. But we can see we're going through the choke. We can see quite a bit of voltage drop to the screens going through the field coil. So this one's kind of interesting because normally you wouldn't expect that resistor drop until after the screen, but this is the way this one was built, so I'm not going to change it or modify it. The good news is, you know, I'm getting audio, so we'll continue on in optimizing this as built. And the only thing I'm going to correct if it's wired incorrectly is the humbucking coil and the field coil, so that they are out of phase and cancel. So yeah, that's what I'm going to do next while I'm waiting on this pot. And of course, this is an antenna. It responds a little bit because it's disconnected. That is the what goes to the tone control potentiometer. So the good news is we have the tubes installed. The electrolytics are working. They're filtering. I'll also put the each of the plates on my scope and see how good the actual filtration is and what the actual signal is like out of each plate, to make sure none of that noise is coming from the audio path. But I don't believe it is. I strongly believe it's that field coil and humbucking coil are out of phase. So I'm sorry, in phase. They should be out of phase to cancel. So I'll work on that a little bit more, and then I'll refine my document. It's got a little bit of chicken scratch on it now because I have started working on documenting all of the voltages. Let's look at something really quick. I want to see about how much power at idle, of course. We don't have any signal induced, but let's see what our voltage is. So if you'll remember, the resistor for the power tube cathode is as banded 330 ohms. This resistor actually tested, its actual value is 375 ohms. So let's see what our voltage is at the cathode. Help if I put the meter on voltage. And let's see what we have here at the cathode. So 10.75, looks like 10.75 volts. Yeah, 10.75, let's call it. So doing the math, that's going to be around 28 milliamps, I think, in my head. So 28 milliamps, and let's see, what is our plate to cathode voltage? So our plate to cathode voltage is 278. So 278 times 28 milliamps, it's going to be around 7.5 watts roughly. So I'll do the math and we'll figure out that exactly. But it looks like the idle dissipation is about 7.5 watts on a 12 watt tube. Very safe and conservative. Really surprised at a little bit at how much the screen voltage drop is from that plate. You know, it's 100 volts lower than almost 100 volts lower than the plate, but you'll get some nice compression, and I do have audio out of this, which is comforting, but we've got to solve the noise and we need to get the tone control and switch in. But we've made great progress, and what hasn't made audio for a couple of decades is at least now making audio. So let me work on the field coil, the wiring, just double check everything, maybe clean that up inside. I'm going to get that masking tape off and do that a little neater with some heat shrink. And then obviously we need to complete this section here. But very good progress, exciting. I do expect with the lower plate voltages and the values that at least I see in the blueprint on paper, I think we're going to get a little bit of dirt out of this amp. Let's look real quick. I'll show you. Let's see what our cathode voltage is on. This is a shared cathode. Let me be careful here. Okay, 0.442 volts. This is the shared cathode on the 6SC7. So, yeah, it won't take a very strong signal before we start getting some grit. So, anyhow, the 6J5 is pretty traditionally biased as we would think of it. Let's see what that cathode voltage is. There we go. So get my pins, my leads right here. So 1.2 volts, very typical. So that's what's driving the power tube. So yeah, we see our power tube is dissipating 28 milliamps. We know our plate voltage, we know our screen voltage, we can see every tube is conducting with the meter. We have audio, we have a nasty buzz, but wow, I am thrilled. Next step is, yeah, we'll go through this field coil, just tidy this up and make sure that our phases are correct, and I'll come back and rejoin. Let's get that solved, and maybe I can get this switch put in at the same time when we revisit this, and we'll see how operational it is. But here we have it, a 1946 transitional Fender amp. This is the classic Woody, the walnut cabinet, 10-inch field coil speaker, Model 26 nameplate, but it is not a Model 26 Deluxe. It is a hybrid Deluxe front end and single-ended early Princeton output section. So with some fairly odd values for biasing, particularly the Deluxe front end. And yeah, other than that, it's fairly straightforward and understandable, but the audio that I heard was encouraging, and wow, I'm almost speechless in the sense that just being able to work on this is such an honor, and I'm a little bit beside myself that all of these original components have not drifted off terribly or are non-functional. The electrolytics, of course, are more understandable, but everything in it is going to be retained original other than the electrolytics in this pot. Hi, this is John. I'm back, and we have the amp completed. So a little explanation. So I had to work on the source of the noise and the noise reduction. So I did clean up the primary wiring inside the cabinet and did heat shrink. I did not change the polarity of the wiring, just cleaned it up and connected it with heat shrink tubing. But I did have to work on the sends and returns here to get the field coil and the humbucking coil out of phase for cancellation. So that has been corrected, and then I will show you on this side here. I cleaned these up and redid these connections so they're real nice, smooth, and good solder joints. So we put this back in, and let's turn it on. I've got instrument plugged in right now. We'll set the tone at noon and the instrument volume at noon and give it a second to warm up. There we go. So very, very quiet. So in humility, what I thought was really not intuitive, did not make sense to me, that is part of the noise reduction. So the cap that was in it, that was kind of just tacked in, and that basically came right out, is this one right here. It's not a like kind as the rest of the amp, but this cap is actually bad, way out of tolerance, and I suspect it has some DC leakage. But anyhow, long story short, after a lot of troubleshooting, what I elected to do to keep this all period correct and essentially have it wired exactly the way it came in was I just repurposed what was the death cap that was no longer in use. So I took this Mallory here and I installed it where this one was installed, and voila. So let's listen real quick. I'll just strum a D chord real quick, and then we'll work on getting a sound test put together. But here we go. So you can kind of hear the richness of it. It doesn't have super high output, but I didn't expect that either. And the tone control does work. It goes darker and much brighter, so that is effective. I got the new pot in with that switch, so you turn on, and that's sort of the bright. You can hear it darken, so that's fairly effective. And then the microphone input also works, so pretty excited. Anyways, thank you for joining me on this journey. What a piece of history. And we are all basically, other than the electrolytics and having to replace this pot and switch, it is all original, the resistors, coupling caps, and then the modern electrics in the vintage container. So I am thrilled. It is operational. Both channels work and all the controls respond. And the noise floor is actually very low right now, so on both sides. So very pleased, and join me for a final sound test. Hi, this is John. Welcome back. So I have the chassis in the cabinet now, and the restoration project is complete. But what I thought I would do before we do our final sound test is go over the as-built. And as I was going through this and learning a tremendous amount, I want to talk about basically the opportunities that I see in it. And when I say that, I don't want to be critical in any way, shape, or form of the way this one was built. It's clearly transitional, experimental. I'm sure some learnings came out of this that were extraordinarily valuable. That said, let's look at this particular amp and maybe some of the opportunity that it has based on what we've learned. So if we keep the field coil speaker, there's really no way of eliminating the fairly significant voltage loss it creates. If you remember right, the plate voltage was around 380 volts, which is fine, and our screen voltage, or our drop, or our voltage at this node here was 305 volts, about 75 volts less than the plate. So let's say this was my amp. And what I would do immediately is I would run the screen off of this filtered choke cap node right there. Then I would drastically lower the value of this dropping resistor, probably to like 4.7K, so that I had higher voltages to drive these plates with on the 6J5 and on the 6SC7. So that's what I would call change number one, really the voltage rails and the voltage drop experienced. Change number two would be I would try to find a way with the existing transformer to find a different turns ratio to reduce the plate load on the 6v6. This plate load is really high for a single-ended 6v6. I'd be targeting 5K, 5.5K. So it should basically be a fourth of what it is. There are a total of 6 secondary taps on this. I'm using the 2 that were used as it came in, but I'd be very curious to see if we could find some other turns ratios that would give us, a 5 to 6K plate load on the 6v6. That would really let this tube come alive. So that would be the second thing. The third thing is, as built, its idle dissipation was about, I believe, 7.5 watts. I would change the value of the cathode resistor to drive this at about 85 to 90% of its dissipation in single-ended mode. Still be conservative, allow for fluctuations in line voltage, but we could really get this 6v6 pumping out a lot more than it is if we change the load, drive the screens with a higher voltage, and have higher idle dissipation. So that's sort of that. Then on the front end of the amp, I would make it like Leo Fender and his team ended up making it in the Model 26. They obviously came to that same conclusion. So I would reduce the value of these grid stoppers to 75K, and I would change the bias on the 6SC7 to use 250K plate load resistors and the 1.5K shared cathode resistor. That will give you a lot more headroom than you have. You really need to roll back your guitar to get a clean signal. And with a full volume signal, it's dirty just the way it is. Remember the cathode voltage here was only 0.44 volts, I believe. So I would definitely do that. And then obviously more plate voltage and different bias would really help that front end and your clean headroom. Wouldn't make any change here. This biased and where that is, I like it. And then I would, coming into the 6v6, I'd probably put a 1.5K grid stopper there. So when you do have some breakup, that would help that scenario. I think lastly, and it's because this power transformer has one, this power transformer actually has a center tap for the heaters, but it's not used. One side was grounded and the other side had the 6.5 volts loaded. I would make use of that center tap. I would either put an artificial center tap or make use of that center tap, and I would balance the heaters for these two tubes and mind the lead dress in a significant way. So if I were looking at this amp strictly from an opportunistic perspective, those are the things I think would make a very material difference in the performance of the amp. Now, it in its own way, it's beautiful as built, but by my own nature and how I'm wired, I would find every opportunity in here that I could. So, yeah, in review, the plate load is too high. We've got, I believe, too much voltage drop here. I think the screen is attached really in a non-optimal position. We could add a grid stopper to the 6v6, change the biasing here, and really leverage a quieter heater wiring. But all in all, I'm going to make one more pass. I'm going to redraw this one time, clean up my chicken scratch, and the owner here will have a complete blueprint of this amp as built, and then we'll move on to our final sound test, which I look forward to. So thank you for watching, and I'll be right back.
Okay.
Nice. All right, let's try the mic. The mic channel real quick.
Okay.
And you'll notice it's a little bit brighter. Yeah, give that a try.
Okay.